there are families of galaxies called galaxy clusters. Is the Milky Way in a galaxy cluster? What's the name of the galaxy cluster? The local group, where everybody knows your name. Yep. So I've got some pretty photographs for you. This one is called, oh, I almost said Mickey Mouse, but it's called the antenna galaxies, a pair of galaxies that are interacting. And I think in the video it talked about kind of these black holes then probably merging to form something, a new galaxy that's even larger. We have a few terms here. The term is merger. In a minute, I'm going to add one of my favorite terms in this topic is cannibalism. Okay, merger is when the size are similar, and cannibalism is simply where there's a big one and it's a little one is being eaten. I'm talking about galaxies here. So this is the antenna galaxies in the visible region. Okay, this is a close-up of the antenna galaxies. And you can almost see these, what we call these nuclei of the galaxies. It's just beautiful. Now just try it. So galaxies interacting, right? We're going to take a closer look at these pairs of galaxies. We have Messier object 82 and 83. Okay. So these are the same kind of field of view. The difference is this one changes. This is in, is it radio waves, I want to say, B? Yeah, in radio waves. And the radio waves gives you a sense of where the gas is. This one's visible. You can't see the gas, but can you kind of, it's almost like I say swapping spit, okay? Like the material is like, it's more than the eye would look at up here. This one actually is just a close-up of this little guy right up here. Isn't that cool? So galaxies dancing. This one's neat. I think it's called the tadpole galaxy, where you see kind of a tail of ejected material from the galaxy. Okay. This one is called the mice galaxy. It's a pair of galaxies, and gravity kind of makes them dance and squish out material. I just think that is so cool. This one, let's see, E. Pair of galaxies, they're fixing to merge. Again, whenever we talk about merger, kind of think of similar sizes. So this is not photographed. This is kind of what a computer said with regard to what we know about galaxies and gravity, what would happen as these two galaxies interact similar sizes. You can kind of see them swirling and dancing, kind of their spiral arms being affected. And the end result is, does this one right down here, what do you think? How many people think that looks like a spiral galaxy? How many people think that's like an elliptical galaxy? Could be an elliptical. So they change kind of who they are. Okay, galactic cannibalism. Dun dun dun. Yep. I'm kind of reading the caption. It's talking about the dust is the smaller galaxy being cannibalized, I believe. So these two are talking about the same object. What appears to be one object, if you look closely, these are actually the hearts of the galaxy. These are the two nuclei. What do you think, black holes? All right, family of galaxies. An assortment of galaxies that are gravitationally attracted to one another in a group. Now these interactions takes millions of years for these pass-bys in the matter to kind of go from one to another. So this kind of looks like the Hubble view, kind of that deep sky we looked at in the Big Dipper. And these little dashes are galaxies, not stars. One of the things, okay, so how do I say this without, do these look kind of ugly? Well, yeah. And the farther away a galaxy is, does that mean that it's more of a baby galaxy or an older galaxy? It we're seeing it as it was a baby. Yeah, as it was a baby. Because remember we talked about this, it takes light so long to get here. So the caption, if this caption, blah, blah, blah. How far away are these? Oh yeah, here it is. Okay. So these are galaxies that are 8 billion light years away. 8 billion light years away. So it takes 8 billion years for the light to get to us. So there's that lag time. Okay, so these are baby galaxies. So if we put the age of the universe when space and time and matter and energy unfolded at about 13, or maybe 13.5 billion years ago, 13 minus 8 is, help me out, 5? Okay. So these are what matter in galaxies would look like 5 billion years after. This is a galaxy called Centaurus A. Is this one of the ones I think that is interacting? No, sorry, I got this mixed up with another one. This semester, I'm not emphasizing it, but the video talked a little bit about active galaxies. I don't know if you caught that. Active galaxies versus quiet galaxies, kind of like active sun versus a quiet sun. Active galaxies, their supermassive black hole is feeding. I don't know if you remember that in the video. Stars fall into the supermassive black hole it's active. So this is an active galaxy. This is not 8, but 10. 10 billion light years away. Okay, sometimes I think the word when we get to this topic is going to be disturbed and just look kind of disturbed and kind of crazy, kind of chaotic. Train wreck of galaxies. All right. Oh, very good. I think the next set of slides, I do have a few videos. I'm actually going to show the video that I started to show and then didn't show if we have time at the end. So, oh man, that all came up at once, didn't it? I don't have any builds. Does this look like the right slide? Yeah. Okay, good. My thing just froze. Oh well, we'll just go with it because we need to get a slide past this one. So, very busy slide. We, in order to understand the Earth's position as it orbits the sun, we kind of need to know a little bit about scale. We need to know distances. We need to know an average distance between the Earth and the sun. Kepler did a lot of work and came up with the idea of the motion of the planets, came up with some laws of the planets as they orbit the sun. Okay, distance is important in all of that. So with regard to distances, let's see if my pen works. Oh, it's Monday. Wow. All right. That would be a negative. So one of the things about distances is we could use what's called radar imaging. We didn't do much with radar. You know which planet, we did a little bit with radar. Which planet could we not see through the clouds and had to do sort of send down a radio signal, look for the reflectivity? That's letter V, Venus. So we did do a little bit with regard to radar. If something's close enough, you can send out a signal, and actually that's how, if you're into severe weather, and when we are looking for potential tornadic activity, we do reflective radar. But it has to be relatively close. Another way of determining distance we talked about was parallax. And remember the way parallax worked is we can know distances to relatively nearby stars. You guys told me on your test, your last unit exam, right? Is if it's a relatively close star, when the Earth moves, it will look like it's moved against the background star. Okay. Well, we have to take it up a notch. And actually, we can use parallax to nearby stars, but there gets a problem with regard to resolving the motion of the star. The star won't move because it becomes a part of the background stars. So now we're taking it up a notch, and we're going to apply this idea of using a standard candle. Using a standard candle. So I'm going to go ahead, and I think I wrote this the other day, that I said brightness, or pair of brightness, that would be your M, okay, is related to your luminosity, how much it's pumping out, divided by 4 pi, the distance squared. So this means as it gets farther away, it's dimmer, okay? As it gets brighter, it's brighter, okay? This is how much energy is pumping out. We could rearrange this and come up with, like you see there, the distance is the square root of the luminosity divided by 4 pi, the brightness. So what this means is, if we know how much energy it's supposed to pump out, okay, and we get a fix on how bright it is, remember that's the magnitude, lowercase m, we can plug it in and get to distances. So there's various situations when astrophysicists, as smart as they are, understand or know what the luminosity of an object is, and that makes it a standard candle. So we have this assortment of standard candles. So, oh wow. Well, I know there's more than one slide. Let's see what this one does. I'm going to kind of walk you through. None of my builds are working. Isn't that interesting? Interesting / frustrating. I wonder. Oh, well. The other thing, oh, maybe I didn't put builds in. Another thing I need to mention, though, is if you have printed out this particular part, I did a bunch of kind of changing the words where they are. It's still the same words. What does this diagram over here look like? An HR diagram, very good. And what are those diagonals? I know one's red and one's blue, but what are those diagonal dots? Main sequence stars. Yep. First Brian Russell would be so excited. Yep. Has anybody seen the Seven Sisters this semester? Mm-hmm. Yeah. Seven Sisters, actually, it's an open cluster, right? Seven Sisters and the Hyades. And the Hyades, they're both in Taurus, the constellation Taurus. The Hyades are kind of where the V is, kind of, and it's right there. Okay, so which one is brighter? It's an HR diagram. Which cluster, the red one or the blue one, is brighter? Well, they've kind of given you a hint. If we take this star, these are analogous stars here on the main sequence stars. Which one would be brighter, this red one or this blue one? This blue one, exactly. So the blue one is brighter, the red one is dimmer, with kind of analogous sort of star. So this is a situation we're not necessarily going to use that, although we could. But what they're saying is it is dimmed by 7.5 times. So the Pleiades must be, they did the math down here, we're not doing math, but it ends up being a square of. So you have to take the square root of 7.5. So the Pleiades actually, because they're dimmer, are 2.75 times farther away. Okay. We're kind of using the Hyades as a candle, standard candle. This is what it should be. It's this much dimmer. This is the amount it's down. We take the square root of that, and we actually have a factor to how much farther away the Pleiades are than the Hyades. It's funny because a lot of you probably you saw Seven Sisters, but we didn't get to see the Hyades much because they weren't rising when we were out there. But they're pretty dim to me, I think. It's interesting to see they're actually brighter. So this is a way we can actually get to relative distances anyway. It's called, you told me main sequence? It's called main sequence fitting. Oh, that one worked. So that's one way. Now this one, remember we talked about, let's see, I can ask this in the form of a question because it's not up here. Do you remember what guy, it's always about guys, right? What scientist actually did this little bit with finding how far away the Andromeda Galaxy is? Which one is it? Starts with letter H. Nope, other H. He's got a famous telescope. Yeah, it is Hubble. Yep. Hubble used the technique that actually, I think it's Henrietta Leavitt found. And it just amazes me because galaxies just look like wispy sort of clouds, but if you have the right equipment or have the right tenacity, you can actually see a star doing a variable, being variable. A single star in a galaxy, and that's what Hubble did. So this one is actually showing the variability of a Cepheid variable star. So the way this works is, of course, if the hump is up, it's high, it's bright. If the hump is down, it's dim. So it kind of gets bright, dim, bright, dim, bright, dim, bright, dim. And the period is 50 days. Now, not all Cepheid variables have a period of 50 days. And as it turns out, their period actually can be linked right back to their luminosity. Okay. So this is a bunch of Cepheid variable stars. And along the x-axis now, we have period. So here, for instance, a Cepheid variable that has a period of 30 days would have a luminosity of this. Okay. So now finally we're ready to plug and chug. We have our luminosity. Of course, we can say how bright it appears. We can do this little math, and we have distance now. That's what Hubble did. So that's a standard candle. It's standard because we can backtrack its luminosity. So this technique, and the way the techniques I'm showing you work are, each technique gets a little bit farther away, because we started with radar, okay, then we talked about parallax, we talked about main sequence spitting, and now we talked about Cepheid variable stars. There's a limitation, well, no kidding, to you being able to see how far away a galaxy is. So I think we looked at this before, and I said I think it's hard for me to tell. I don't know, this kind of looks like a variability. Anyway, amazing. Okay, so another standard candle. I think all those songs will be Candle in the Wind or something. Another standard candle, okay, is something we talked about before. We talked about two types of supernova. And this is the type of supernova that involves the white dwarf. So go back in time. We're talking about a retired star that has a swollen companion and it's getting dumped on. We said that it can get dumped on and just kind of throw off like a nova event, kind of like a blanket, or it can get dumped on to exceed the Chandrasekhar limit and totally blow up, okay, in a supernova type 1A. So if that happens, we know how bright that event should be, because the 1.4 is the standard mass tipping point. So all supernova type 1A events are going to have the same luminosity. The other type 2, where a massive star ends its life, those will vary. But the supernova 1A, white dwarf blowing up, they will all be standard. And it just amazes me again. The dedication of people I see, well, I am in awe sometimes of the custodians. I mean, the dedication you see, we need everybody to do their job. But my point here is that here is a galaxy before the supernova event. Looks like one of those far away ones, doesn't it? What do you think? That was a retired star that got dumped on by its companion to exceed 1.4 solar masses and blew up. So these events are even more luminous, brighter than the Cepheid variables. So we can see these farther away. Here's another one. That's before, that's after. What a rush. And it's like, it'll stay pretty bright for a couple of weeks and then it will decay. Before, now that one's really simple. I've got a friend out at the observatory who I don't know if he knows where every star is, but it seems like it to me. He'll look through Dave. You know, we was looking for Uranus the other night, and but he will find these little explosive events, and they look like a new star, but then they'll die away. Okay, so these are supernova type 1A. So it's standard Volt. So we can see approximately 10 billion light years away. Well, that's getting close, okay? So I'm going to make this not our sun, but I'm going to make it us here at the Milky Way galaxy. Okay, so I said a minute ago we saw pictures of 8 billion light years away galaxies and then 10 million light years away. This is a way to understand how far away they are. We know the luminosity associated with a supernova type 1A event. We know how bright it appears. We do the math, we get the distance. Cool. Just beautiful. With Christmas coming up and everything. Okay. Okay, so there's Edwin Hubble looking through his telescope. Oh, I didn't realize this. I should have known. It uses mirrors and not a lens. 100-inch, big reflecting telescope. So let's see what this little video, the videos I have are pretty darn short. Let's check this out. Expanding Universe Now. And it's kind of like, you know, if we go back, I like to put this stool here. Okay, here's the sun. If we go back to just kind of our neck of the woods, one of the things we talked about, maybe for a different reason, is that the stars will make different patterns over like thousands or hundreds of thousands of years, right? I talked about this. Well, kind of the same way or a little bit when we look at those galaxies, think of they aren't always where they're gonna be. Okay. Now we'll talk more about this expanding universe, but do you remember we talked about space-time, the fabric of space-time? Okay, so it's not that, well, it is a little bit, that these galaxies are relocating, but it's also the fact that the fabric of space and time is expanding. Okay. So one of the things we've been talking a lot about here is if something's moving away from you, do you get a red or blue shift? Red, yep, it gets longer. So this is actually like a library sample, and you can kind of look at this particular peak. If we look at a sample of a galaxy, do you see where that little peak, does that match? Okay, kind of have the same shape. It matches over here, but it shifted to a longer wavelength. Okay, a lot of times in physical science we'll use the triangle for the delta, the change in. So whatever this change in, that moving over, that is an indication, that's what we call the redshift. It's an indication of how fast it's moving away from us. So if it's moving faster away from us, the greater the redshift, right? Not moving as fast, the smaller the redshift. And so scientists get really excited when we see straight lines. So like the video said, the farther away the galaxy is from us, the faster it's moving. So you're going to see a plot here in a minute that says how far it is away from us, that's along the x-axis, and what we call recessional velocity, how fast it's moving away from us, is going to be along the y-axis. You'll see the straight line. It gets a little tricky though, I think, because if you're like me, like Mrs. Knight, you said that the Andromeda galaxy and the Milky Way galaxy are going to converge, okay? So how does that work with everything's moving away from us? And I think like this slide maybe says, within our cluster gravity, we still have the local gravity affecting us within the cluster of galaxies. But overall, like galaxies and other clusters are moving away. It gets a little confusing. So the straight line thing I'm going to show you is called, well, I guess it's not the straight line, the graph I'm going to show you, but the phenomenon of galaxies moving away from us faster if they're farther from us, that is called Hubble flow. Hubble flow. So here's that graph I was telling you about. Along the x-axis, we see how close or how far away the galaxy is from us. Okay, and then along the y-axis, we see how fast it's moving from us. So the farther away it is from us, the faster it's moving. We see this. Now, one of the things about straight lines is we can make an equation for the straight line. We can come up with what's called a y-intercept, an x-intercept. We can also come up with the slope, okay? The slope is really important. And as it turns out, the slope actually ends up being a nice cool constant called Hubble's constant. And if you know much about kind of plotting straight lines and using them to interpret data, if you have the slope, you can actually kind of run with it as far as plugging in a distance and calculating recessional velocity or the other way around. So Hubble's law, Hubble's flow, Hubble's constant, Hubble. Okay. But as it turns out, we can actually use Hubble's constant, and I'll probably talk about this in Unit 5. We can use Hubble's constant to gauge, go back in time in a sense, with zero recessional velocity and understand the timing of the Big Bang. We watched that video the other day where, I think this would work, yeah. Where the guy, Philip Bingo, I think is his name, he had like 5 balls, ping pong balls on a bungee thing that stretched. Okay, that's what he was talking about, expanding the universe. And he said that if you're over here, this guy's expanding even faster. If you're over here, this guy's not expanding as much. The recessional velocity. So that's exactly what he did. So this is kind of interesting. This is new to OpenStax. This is kind of looking at a scatter plot of ultimately Hubble flow. You can kind of see the limited amount of distance of galaxies versus how fast they're moving away from us. That was in 1929, and then 2 years later, 1931, and began to, this is Hubble and, who did he work with? Hubble and Humason. They actually got even more data, and I think this would be exciting when you start to see that kind of extended out. You're like, whoa, that's a pretty cool fit. Your what's called correlation coefficient probably started to begin to kind of be a happier sort of thing. It's not perfect, like the slide said. It's definitely a scatter plot, but you can definitely see a trend. So these dots here are galaxies. In the dead center is the Milky Way galaxy. Of course, we are not the center of the universe. But you can see as you go farther from the Milky Way galaxy, the color in red is kind of showing you the Doppler shift. So the more red it is, the more the Doppler shift, the higher the recessional velocity. So this is taken by, part of the project, the Sloan Digital Sky Survey. And this is the Sloan Digital Sky Survey. I've seen a little documentary on this, and instead of like seeing beautiful galaxies and all that, it's kind of distilled down into pinpoints of light and looking for the redshift. Okay. So this kind of sums up, of course, we have the Earth here. This over here would be the edge of our observable universe. Okay, so how can we get the distance of objects? So first off, we talked about radar, like we do on Venus. Okay, we talked about parallax earlier. This is getting a little bit farther. And you can kind of see there's some overlap in these techniques. We talked about main sequence fitting. That gets you down there a little bit. Standard candles, we said using the Cepheid variables. There's a little picture to kind of remind you that. We talked about using type 1A supernovas. Okay, and then actually we can use Hubble's law if we can observe the redshift, observe the recessional velocity. We can pick it off of that calibration curve per se, come down and understand its distance that way too. Now this is, I know we're bumping up against time, but I think we should watch this. Let's see how long this is. It's not very long.